Hello, and welcome to another episode of Tech Beyond the Hype, the podcast that explores how the latest advancements in business and tech are shaping the future of work. I'm your host, Anna Salon-Boira, and in today's episode, I'm joined by Johna Till Johnson, CEO and founder of Nemertes Research, to explore the curious and exciting world of quantum computing. We take a deep dive into the quantum world, breaking down the differences between quantum and conventional computing, the potential business applications, and risks that quantum poses to traditional cryptography. I had such a great time recording this episode with Johna, and I really appreciated how she broke down what had previously felt to me like a really inaccessible and complex area of tech. She really helped me to understand quantum computing and turned it into something that not only makes sense, but really feels like an exciting area of innovation. I hope you'll enjoy the episode as much as I did. So now, without further ado, please welcome the wonderful Johna Till Johnson. Okay, Johna, thank you so much for joining us here today for Tech Beyond the Hype. I'm so excited to have you on today to talk all about quantum computing. Before we kind of dive in, could you just tell us a little bit about yourself, about your background and what you do for work?
Okay, so first of all, thank you for inviting me on. This is going to be fun. I run Nemertes Research, which is a research advisory consulting company. We specialize in the business and operational impact of emerging technology, and we've been doing this for 21 years now.
How does quantum computing come into your work at Nemertes?
Most of the sophisticated clients that we have recognize that quantum computing is going to come along and going to fundamentally change things the same way every other computing or networking paradigm shift has done. So, right now, the vast majority of people, maybe 80 to 90%, think of quantum computing as kind of a buzzword at best. But the leading edge folks, the folks for whom computational capabilities are a critical differentiator, are already extremely interested in what can we do today? What can we do tomorrow? How do we prepare ourselves to take advantage of this shift? So those are the folks that we're working with. Think about defense organizations, the military, defense contractors, financial services firms, anybody for whom computing better than the next guy is an existential value. Those folks are paying close attention.
Okay, awesome. So you're working with kind of the big dogs in the industry.
We are, and also with folks that you might not expect. For example, advertising companies are very concerned. Obviously, they've already hopped on AI, but they really want to understand where quantum is going to take them as well.
For the average listener, say, imagine we're talking to someone who is not from that background and who has very little understanding of quantum computing. What are we talking about when we're discussing quantum computing, and how does it compare to the computers that we're used to having in our homes and everywhere nowadays?
I think the first thing to understand is it's fundamentally different hardware. So to understand how different quantum computing is, you have to go all the way back to the transistor. Believe it or not, the entire computing industry was built on the insight that you can do an awful lot of things with a physical device that's like a light switch, either on or off. And the entire microprocessor industry was built up of transistors networked together to create microprocessors, which then create intelligence and networking and everything that we have here and now. But it's all based on this concept that the transistor is either on or off, and it's reliably so. So you can set it on, set it off, and it'll pretty much stay there until you're done with it. In a very weird way, you can think of quantum computing as almost the dimmer switch. Instead of on or off, it can be kind of anywhere, with the catch that it won't necessarily reliably stay there. And you might think to yourself, why would I actually want something like that? It seems kind of squishy and nebulous. And in fact, it is. Quantum computing hardware is built on this concept. Instead of bits, you have qubits, which are quantum bits, which can be either on, off, or somewhere in between, just as quantum physics actually allows you to be in sort of multiple states at once. And this concept of multiple states at once turns out to be core to what you can accomplish with quantum computing. So if you're slightly more mathematically inclined, another way to look at it is we all know hexadecimal notation and binary notation. Binary notation is it's either a 0 or a 1, and you represent any number with either a 0 or 1. So, 0 is 0, 1 is 1, 2 is 1, 0, and so forth. 4 is 1, 0, 0, I think. Don't quote me on that. It's been a while. With decimal notation, each digit can be anywhere from a 0 to a 9. So that's our normal mathematics. That's what we're used to. Hexadecimal, you actually throw in a couple of letters and you have 16 discrete states. Another way to think of quantum computing is, let's say you could have all real numbers that could possibly occur in those states. So you might have pi as one of those states. So something that goes on and on and on. So essentially, the ability to have infinite variability in the states is what actually is core to quantum computing.
Okay. I mean, so from a perspective of someone who's never come across quantum computing, or even just myself who has a limited understanding, what you said is pretty complex. And I think maybe it will make more sense if we try and apply it to something more practical. So when it comes to having various different states, what I'm understanding from what you said is that you're able to achieve perhaps a higher degree of accuracy, or that there's more possibilities. Is that correct, or am I going down a rabbit hole here?
Yeah, you're actually going down a rabbit hole. It's actually the other way around. So David Deutsch, who is reliably considered the father of quantum computing, I think he's in his 90s, but still doing research, once said something to the effect of quantum computing gives us the ability to solve any given problem in multiple parallel universes at once. So you don't actually get necessarily greater precision. In fact, in a meaningful way, you get less precision because things aren't as crisp. But the ability to be in multiple states is what's so exciting. So essentially, at a broad level, and I said start with this is fundamentally different hardware. The next step is it's also fundamentally different software because you're solving different kinds of problems. So here are a couple of examples of problems that you can solve with quantum and that you can't necessarily solve with classical computers. And let me take a step back. Classical computers are great at problems such as give me the answer to this problem if there is an answer and it can mathematically be computed within a reasonable amount of time before the heat death of the sun, basically. Classical computing is great at it. Quantum can help, but not really. What quantum is good at is solving problems for which there are many answers and letting people decide which of the many answers is the one that they want to look at. So a great example of a problem that quantum computing can solve and classical computing cannot is something like, why don't you figure out what we call policy hardening? So it's why don't you figure out what all the possible ramifications of this policy are and select the policies that don't lead to a couple gross outcomes. So, for example, since all of us are paying attention to the news, what possible policies towards this other country could we have that don't result in war? Something that simple. And that they may result in lots of other things. And you can tighten up your definition of an acceptable answer up to a reasonable point. But that's what's so brilliant about quantum is you're actually not solving for the answer, you're solving for an answer that works for you, which, if you're thinking about it, is the way humans work. And that's one of the things that's so exciting about quantum is because it's fundamentally very organic. That's the way the universe actually works. There's never any right, absolutely hardcore right. We artificially constrain things into black and white or on and off because that's how our mathematics allows us to manipulate them. But if you have a tool that is perfectly at home in the real universe of pretty good or good enough, now you've got a whole different way to approach things.
Right. That's super cool. Thanks for explaining, because I think it makes a lot more sense now that you've said it like that. It's almost like we've existed in a world where computers are very binary in terms of there's a right or wrong solution to X problem. And we kind of assume that every question will have a yes or no answer because of the way that computing has worked. But with quantum computer, you have the opportunity to have a whole spectrum of different possibilities, which feels, like you said, a lot more organic, a lot more natural, because things don't exist in a binary in general. So it makes a lot of sense.
Well, and exactly. And actually, the only thing I would add to what you've said, and you're much, much closer now, is that it's not just computers. It's also our mathematics, which meaningfully have been based around our computing capabilities. So it's actually very useful to understand that a lot of our problems, like we talk about NP complete and NP hard problems, which have to do with how quickly you can solve them. But the fundamental concept, and that's all a computer science mathematics definition, but the fundamental concept is solve. And so when you change the definition of what it means to solve, your mathematics changes, which brings me to the sort of second piece for the average. I say average. Nobody listening to this show is average. We know this. You're special. But for someone who's not necessarily working in the Defense Department or cutting edge financial services, and you're going, why should I care? Well, not only does the hardware change, but all the software changes too, because all of the algorithms that we've developed are either designed to get at the answer or designed to incorporate clever hacks because we don't know what the answer actually is, or we don't care what the answer actually is. So in some sense, we slowly and laboriously use classical computing algorithms to create multiple possible answers to a problem, but it's a forced exercise. So basically, boiling it all down, different hardware, different software, different problem space. And now you're going, oh, great. Everything I learned in my computer science and electrical engineering classes is wrong. It's not about transistors. It's about qubits. It's not about solving problems. It's about reaching solutions that may be acceptable within varying parameters of acceptable. That's pretty much true. And that's what's so fun and interesting about it, because it changes things the way the transistor changed everything.
So from a business perspective, what are the applications for something like this? And to what degree do you think with a quantum computer, if say you have a business that implements quantum computing, how much does their business decision-making processes need to change around the implementation of the quantum computer?
That is an excellent, excellent question. And the answer is a lot. And in fact, one of the projects we're in early stages on is helping an organization change how to even approach the problems that people are using to address with quantum computing. And so, as if it weren't enough, we changed the hardware, we changed the software and the algorithms, we changed the problem space, and oh yeah, we have to change how we as humans think about it. And of course, the holy grail here is that if you add AI, which is already changing how we think about problems, right before we got on this recording, you just sort of offhandedly said, oh yeah, an AI could solve that. And right now, people are busily going, oh, what things am I doing today that I really shouldn't be doing because an AI can solve that? Well, if you start piling AI on top of quantum, now the world has just changed dramatically. So basically, in order to effectively implement quantum, you need brand new hardware, which companies are making, brand new software and algorithms, which companies are making, not necessarily the same companies. There's a broader network of people, a new way of thinking about the problem space, and training and coaching for people who are mid-career thinking about how to solve these problems differently.
Right. I guess even the language of problem, right? With a quantum computer, it's not even a problem because you don't have a yes or no answer. So it's more...
Oh, it's still a problem. And I mean, just for those of you who are listening who still remember your computer science background, we're all taught that problem types are P, NP, NP complete, and NP hard. P stands for it is verifiable in polynomial time and solvable in polynomial time. That's the kind of problem we all like because it's sort of like, just go compute this and give me the answer. NP is verifiable, that once you've found a solution, you can verify that it's the correct solution in polynomial time, which is essentially finite time. And it is maybe solvable in polynomial time and maybe not. NP complete is like NP, which it is verifiable in polynomial time, but we have no idea if we can solve it at all. And NP hard is maybe not even verifiable and maybe not even solvable in polynomial time. So, okay, this is our little framework that we go look at problems. And this is, by the way, it's still important to have a computer science degree if you're going to be in coding, because if you just go to a coding boot camp or something like that, you won't understand the mathematics behind this, even what it means to solve something in polynomial time. And at a practical level, you might end up trying to solve a problem that's completely unsolvable because you didn't know the concept of unsolvable. So then, when you start looking at these classes, there's quite a lot of NP-complete problems that fall into things like scheduling and logistics, and NP-hard problems. A classic example of an NP-hard is the traveling salesman problem, which is, I have a list of cities, I have the list of distances between each pair of cities. What is the shortest possible route that visits each city exactly once and returns to the origin city? So here's a really interesting example of a different way to approach things. What if you wanted to say, I don't actually need the shortest possible route. I need routes that are short enough. Here's my limits of resources. I need all routes that are shorter than X or something like that. Those are the kinds of problems that you can get an assistance with using quantum. And just to get back to the main point of this, once you take classical computer science, now there's a whole set of classes of problems called BPP and BQP. And BPP is bounded error, probabilistic, solvable, and polynomial time, which are examples that I just gave, which are for classical computers. And then BQP are bounded error, quantum, polynomial time. These are problems that are solvable within a polynomial time with a bounded error probability, which is a fancy way of saying, good enough. So a classic example of this kind of problem is prime factorization, which is exactly the root of cryptography, which gets us into a whole nother discussion, which is why everybody runs around talking about the quantum cryptocalypse. I can't even say it. Cryptocalypse. The point being that there are very defined classes of problems that quantum works in, and some of them threaten existing classes, and some of them are brand new. And sorry if that's super long-winded.
No, not at all. So going back a little bit, you mentioned earlier the scenario of what are the different options that we could take that don't involve going to war. In that example, you said you have various different options that don't involve war, but then that have other repercussions to them. I assume that a quantum computer by itself wouldn't, and I mean, correct me if I'm wrong here, but I'm assuming that a quantum computer in and of itself would not be able to tell you what the repercussions are. But then when you add in the AI, is that where you have the opportunity to kind of understand the repercussions of all the different options that you might be able to take?
Close. Depending on how you structure the problem, you actually could get the repercussions. Think back to David Deutsch's comment. You're solving problems in parallel universes. So you ultimately will end up with lots of different scenarios at the end. The classical science fiction is, what if I turned left instead of right at this street corner? Well, then your life splits into two, but you have a full and complete life in both cases. And in the quantum computing world, you would know what each one entailed, who you met, who you married, what you like for dinner, how that changed. And then just imagine all the numbers of branches that possibly could occur in your life. And you realize, ooh, that's big. So one of the questions is, and it's always one of those metaphysical questions, like which one of these branches actually matters? Which ones matter the most? Is it possible to come out with a handful? This is a conceit of a lot of science fiction, that most of the decisions don't really matter and don't really change your life, but a handful of them do. And these are the major decisions that would. One very important use of AI is to really help stack rank that and sort through that very, very quickly and figure out, okay, these are the decision points that make the most sense. And so you can zero in and say, okay, we will send our person to that city, not this city, because it turns out that the outcome is going to be vastly different based on the city, but it really doesn't matter whether he meets with or she meets with person X or person Y, because the outcomes don't really change based on that. To solve a problem like this, you have to say, okay, what are all the decision points, knowing that in the real world, they're infinite? And then what are the ones that matter? And how do we sort through the ones that matter and stack rank them so that we get to these outputs and we know what to change? So yes, AI plus quantum can help an enormous amount here. I don't know, and I don't think anyone really knows the full extent to which AI and quantum can interact.
Right. Sure. I guess, we're pretty early days with both, so that makes a lot of sense. You mentioned earlier about the crypto, I can't think of the word that you use now.
Quantum cryptocalypse. Yeah.
That's it, the quantum cryptocalypse, which is the idea that quantum computing would essentially break all cryptography when it comes to blockchain. Is that right?
It's a little broader than that. Essentially, the question is, does it break conventional cryptography? And these are algorithms like RSA. The core root of these are, it's really hard to factor really large prime numbers. So timeframes that are bandied about with conventional computing, cracking 2048-bit RSA takes, approximately, give or take, 300 trillion years. With quantum computing, you can do that soonish. At the beginning of this year, I wrote a paper saying, well, is it going to happen? And the answer is yes, but not right away. So hypothetically, quantum computers could crack 2048-bit RSA much faster than conventional ones, say in a couple hours or even seconds. And the key point, sorry, I didn't connect the dots here, but RSA is the root behind a lot of cryptography, protecting data in the cloud, for example, not just blockchain. Blockchain relies on cryptography, but so do an awful lot of other things. So that's the relationship there. I wrote something which turned out to be incorrect. I wrote, the short version is therefore that it will require years, perhaps a decade or more, of development before cryptographic algorithms will be crackable with quantum computing. Not a negligible time frame, but not one requiring instantaneous response. Well, at the time I wrote that, there were some Chinese researchers who had claimed they had already done it, but when you went digging into it, they not only hadn't broken it, they kind of used a very, very shady way of making it look like they had when they hadn't. They said, there's an algorithm that's been around for 30 years that talks about factoring integers using hypothetical quantum computers. It's called Shor's algorithm. But their research worked on something called Schnorr's algorithm, which is a classical algorithm and has nothing whatsoever to do with quantum computing. And the whole article is about Schnorr's algorithm, but they preface it by saying, Shor's algorithm says that quantum computing can crack cryptography.
So sneaky.
So sneaky, I know. And I was like, really, guys? So I was feeling pretty proud of myself that no, it hasn't been broken and no, it's not going to happen. And then here in the United States, the National Institute for Standards and Technology prides itself on being ahead of the curve when it comes to things like this. So they had, in July of last year, issued something called quantum-proof cryptographic algorithms. And they were super proud of themselves. Like, here's our 3 algorithms you can go use and be safe, confident that you are protected until, for your lifetime against quantum attacks. Well, this past spring, some Swedish researchers actually used a combination of quantum and AI to crack those quantum-proof algorithms. And I kind of had egg on my face because literally I had to write almost back-to-back 2 advisories, one saying, no, it hasn't been broken yet, and the other one saying, well, actually, hold that. It kind of has. And the mechanism is something called a side channel attack, which essentially refers to the fact, very, very clever of them, but that they used AI to do things like look at the temperature and the power consumption of the computers that were crunching along and use that to guide the directions that the quantum computers went, because they could figure out what some of the results are based on the physics of the computational processing. This is a well-known thing. It has a name. It's called a side channel attack. And I essentially said, when NIST was creating these quantum-proof algorithms, they should have thought about the possibility of a side channel attack and hardened against them. So far, NIST has said absolutely nothing about this. So long story short, the date for the quantum cryptopalypse is sooner rather than later, and getting sooner. All the best experts in the world said it's going to be quite a while, including myself. And then now we're like, oops. So, and again, side channel attacks are not something new. Anyone who's been working in cryptography knows this. And in fact, a complete side note, but I love digressions. I was absolutely stunned a couple of years, well, maybe a decade ago, when the news came out that apparently you can recreate an entire conversation if you have a good enough ability to video. Like if you've got an empty potato chip bag in a room where people are talking, you can look at the vibrations of the potato chip bag and recreate the whole conversation. And I was like, whoa. And anyone who's been seriously working in intelligence or cryptography just laughed at me and said, wait, you just noticed this? The rest of us have known about this for 50 years. And I'm like, well, now that I've found out, I'm scared.
Wow. Wait, I'm confused about the relationship between, and maybe I'm misunderstanding, the potato chip.
Mm-hmm. Yeah, how do potato chip bags connect with quantum computing?
Yeah, like the sound wave, because I understand what you're saying and it's awesome and very cool, but I don't understand the relationship between that and the cryptography.
Okay, so A side channel attack is when you look at something that is not directly related to the computational algorithms. So kind of the way to think about it is here you have this computer and it's crunching away on something or other, and it's very important and it's following mathematics and algorithms. And now you've got a thing which is sitting next to it and going, you're getting hotter and colder and hotter and colder and vibrating this way, kind of like the potato chip bag. The potato chip bag, it's the relationship between the vibrating potato chip bag and the fact that I am giving you an international nuclear secret, right? Potato chip bag has no idea. It's just sitting there going bzz, 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 bzz. And the side channel attack is watching your computer go bzz, 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 or the equivalent of that. And the side channel analysis has no idea what's going on inside the algorithms, but by correlating the two, it can drive the quantum computing algorithms to go in the places that are most likely to generate results. So it shortcuts a lot of what, if it was just going through brute force and not getting that physical feedback from the real world, is kind of a good way to look at it.
Right. So it's like the potato chip bag is able to detect, or through the potato chip bag and the vibrations of the potato chip bag, you can then detect the kinds of conversations that are being had around it in the same way with cryptography.
Exactly. So basically, the common theme is that you're using something that has nothing to do with the issue at hand and nothing to do with the mathematics or the analytics or the abstractions to kind of figure out the answer. And because this is so well known by people who aren't me, it's the kind of thing that NIST really should have thought about before they came out and said, we have a quantum proof algorithm, because somebody in the room generating that should have said, hey, is this thing strong against side channel attacks? And they should have tested it or figured out how to come up with the answer. So tying potato chip bags and NIST and quantum cryptocalypse together, what you get at is a sense that things are changing extremely quickly, and things that didn't used to be considered possible or used to be considered possible on timeframes that don't matter, those timeframes are compressing faster than even the experts thought was going to happen.
Right. And so I guess I can imagine what your answer is going to be to this final question. But let's say we're looking into the future, 20 years down the line. What's the state of quantum computing?
I'm trying to actually answer that in something that's meaningful to me and to anyone listening to this. I can safely say that for sophisticated organizations, there will be a quantum computing team. So people who have specialized in it, have degrees in it, and are leading the charge in their organizations. I can safely say this because they exist today. I've talked to them. So there are going to be more of them. Another category of problems that we didn't touch on is simulations. So simulating anything real world, or as my colleagues like to say, hey, finally we'll get accurate weather prediction. You can imagine what kinds of companies care about this. So if you're an oil company, you want to know exactly where to drill to find the oil. If you're an insurance company, you want to know exactly where to look to find out which of the 100,000 people you're looking at is going to die of cancer or whatever. So for people doing those broad, vast simulations, I would say quantum computing not only will be, but is integrated into their core business. For quite a lot of other organizations, it'll be still part of a separate group the way high performance computing is today. So to answer your question, for the next couple of years, it's not like you're going to go buy your friendly quantum enabled laptop and slap it on your desk and suddenly solve these parallel universe problems. That will come. If you think about it, people like to joke about the fact that your phone has more computing power than the most advanced computer that was ever even envisioned in like 1950. And there's plenty of people walking around who were adults in 1950. I was actually talking to my mother, and she's 97, so she's a little bit on the outer edge, but she can talk about 1950 as though it were yesterday. So in the lifetime of people who are adults today, quantum computing will vastly change almost everything they experience.
Ooh, I felt a little rush there when you said that. It's very exciting, but also a little bit, when you're looking at the abyss of things that you don't know looking into a future that really you can't predict. Feels a little bit like that, but that's very exciting at the same time.
It is. And actually, just another side note, I actually had to stop myself from putting an asterisk and a footnote on that, because I hate to say it, you can feel free to edit this out, but I was thinking that is if we don't have, the Carrington event 2.0 and electromagnetic pulse takes away all electricity and all computers for all civilization, in which case 50 years from now, we're probably going to be doing very different things.
Ooh, that's a very funky place to end the podcast episode.
Well, that's why I stopped and breathed, so you can edit it out if you wish, because, the problem with being a scientist is you want to say things that are really crisp and provocative and things will be different. And then you realize, yeah, but actually this thing could happen. So everything I just said is invalidated. So, and then you feel required to say that. I don't think, periodically this one pops up and everybody goes, oh my God, that could happen. And then everybody does the same thing and goes, what can we do about it? And the answer is kind of not quite nothing. If you work for, and I do have friends who work in the energy industry, it's sort of like, well, you may want to think about the dark start generators, because it turns out, interestingly enough, that there are only a handful of electrical generators that can be restarted if they have been shut down. So we might need more of them, just saying. But other than that, if you don't work in the energy industry, there's not much you can do about it.
Well, thank you for your honesty. I like the it's a dark possibility, a possibility nonetheless. One that I'm going to hope will not happen. I'm sure more people listening are as well. Well, on that note, thank you so much for joining me on the episode today. It's been an absolute pleasure having you on as a guest. I've learned a lot about quantum computing. You've really opened my eyes up to what I thought was very, very complex, but now is seeming much less complex. So thank you so much for joining me.
You are very welcome. And I love to hear that, because that's what I try to do. I try to kind of distill the essence of things down so people can understand the major impacts, given that I'm going to be losing some of the subtleties and nuances along the way.
Well, I think you did an excellent job. So thank you very much.
You're very welcome. It was great fun. Hope to do it again sometime.
So that's a wrap, everyone. And not just for this episode, but for season 1 of the show. Thank you all for joining me on this podcasting journey. We're going to take a short break from the series for now, while we work on producing the first few episodes of season 2. If you like what you've heard so far and want to hear from more industry-leading experts about the future of work, please do make sure to like, rate and subscribe to Tech Beyond the Hype on Apple Podcasts, Spotify or wherever you like to listen. Help spread the word about the show by sharing the podcast with friends, colleagues, your boss. Basically, anyone you think could be interested in what we have to talk about. We would be so grateful if you can get them tuned in. Tech Beyond the Hype is a Tech Target original production.